Alright, so this is part B1, and we're going to be deriving differential equations for the mole fraction of water and air, and the temperature of the gas and the water in a cooling tower. So I did a drawing here to show the situation that we have. So we have this cooling tower with some packing with specific volume A, which is square meters over meters cubed. We have temperature of some water going in, and then water going out, and then we have the temperature of the gas going in, the gas going out. So we are going to be deriving some equations to find this. So first we need to find the gas flow rate and the liquid flow rate. So the gas flow rate is just the kilograms of air per meters squared times seconds. And then we have our liquid flow rate, which is the same, but it's kilograms of water per square meters times second. All right, so we're going to be making some differential equations, and we're going to be looking for it in relation to the height of the cooling tower, so how it changes over the height of the tower. So we're just going to start with the gas flow rate. So we're going to have, because we're going to try to find the equation for the mole fraction. So we need the flow rate of the gas, and we want that in moles so we can get the mole fraction, so we're going to have to divide by the molecular weight. And since we want it in terms of, like, we want the mole fraction, we have to have the mole fraction, so the mole fraction of water. And we're going to need to multiply by the cross-sectional area to fix our units, and then that's going to be the change in that, and so that's going to be equal to the we're going to be doing it in molar flux. We're going to be using that equation, so we have the mass flow coefficient, mass transfer coefficient, times the concentration at the interface minus the concentration in the atmosphere. And we're going to have to multiply that by the specific volume that we are given. We're going to want to get an actual volume, so we're going to have to multiply it by the cross-sectional area and the change in the height, so dz. This here, change colors so you can see better, is essentially constant throughout. So you can take that out because there's no really change, and same for the area, it doesn't really change, but it cancels out because we have area on both sides. So then we can also divide by the change in height to rewrite our equation. So the change in the mole fraction over the change in height is going to be equal to some new quantity. And if you look at this chunk here, it's just the molar flow rate or mass flow rate for the water, so we can just rewrite that as mass flow rate of water, or the mass flux of water. And this actually has to be the negative, so it'd be the negative mass flow rate, mass transfer, mass flux, sorry. Okay, so we're just going to rewrite this. So we're going to have a negative, we're going to have our mass flux times the area, the specific volume, I mean, times the molecular weight divided by the gas flow rate. And that's going to be our first equation. That's the equation for the mole fraction in the air. And now we need to move on to the temperature of the liquid. So we're going to be using our liquid flow rate here. And we're going to have to use enthalpy for this because the enthalpy, the change in enthalpy is going to be equal to 0. So you can use that to say that the enthalpy of the liquid phase is equal to the enthalpy of the gas phase. And we can use that to manipulate some equations. So we're going to have the change in enthalpy of the liquid phase, I guess it'd just be the water phase, and that's going to equal the liquid flow rate times the specific heat capacity of the liquid phase. Excuse me. And then we're going to have to multiply that by the change in temperature, and we also have to multiply by the cross-sectional area. And so we can actually expand this equation a little bit. That way we can actually work with unknowns that we have. So we're going to use the heat transfer equation. So the heat transfer coefficient times the temperature of the gas minus the temperature of the liquid. And that's because, and then, yeah, we're going to do that. Then we need to subtract the heat of vaporization because the temperature of the water is going to decrease. It's going to cool. And we're going to multiply that by the mass transfer, the mass flux, sorry. And we're going to have to multiply this whole thing by the specific volume and the cross-sectional area and the change in the height. And then if you look at this, you can see that the areas will cancel, and we can rearrange this a little bit, and that should be the temperature of the water. I believe, yeah, that should be the temperature of the water. So then we can manipulate this a little bit more. We can divide the change in the height over, and then we will get this new equation. I will just rewrite it down here. So we get the change in the temperature of the water over the change in the height of the cooling tower is going to be equal to the specific area divided by the liquid flow rate times the heat capacity of the liquid phase, and it's going to be multiplied by our quantity here, the coefficient of heat transfer times the difference in the temperature of the gas and the liquid, minus the specific heat times the mass flux. And that will be our equation for the temperature of the water. And now we can move on to the temperature of the gas. And we're going to be using the same principle that we did up here. The change in enthalpy is going to be 0, and the enthalpy of the liquid is going to be equal to the enthalpy of the gas. Let's go down a little bit. So we're just going to take the equation for the change in the enthalpy of gas. It's going to be equal to the change in the gas flow rate, and we're going to multiply it by the heat capacity of the gas, and then we have to multiply it by the area and add the heat of vaporization time, and multiply it by the gas flow rate and divide it by the molecular weight, because we need to get it in the moles, and multiply by the mole fraction of water in the gas. Oh, and then we have to multiply by area again to keep our units the same. And this will be equal to, similar as to what we did above, the heat transfer equation for this would be the coefficient times the change in the temperature of the gas times the difference in the temperature of the gas and the temperature of the liquid, and that is going to be multiplied by the specific volume and the area and the change in the height of the cooling tower. And then we're going to have to subtract the heat of vaporization multiplied by the mass flux, and again we're going to have to multiply by the specific volume times the area times the change in the height, and our areas will cancel, and we can rewrite this. Let's see. So you'll have so the gas flow rate and the heat capacity of the gas, they won't change as the height changes of the tower, so they can just be brought out. So we'll just have the gas flow rate times the heat capacity, time or plus, no, not plus yet. It'd be times the change in the temperature of the gas divided by the change in height, plus the heat of vaporization vaporization times the gas flow rate divided by the molecular weight, and that's going to be multiplied by, because we have these two equations which are the same, we can replace that with the change in the mole fraction divided by the change in the height, which is just equal to this, as we said before. The whole thing's to my page. Okay, so then we're just gonna clean it up a bit and just have the equation on the right hand side. So that'll be the change in the temperature of the gas over the change in the height is equal to the specific volume times the heat transfer coefficient divided by the gas flow rate times the heat capacity of the gas, and this is going to be multiplied by the difference between the temperature of the gas and the temperature of the liquid. And that's the last differential equation we will use. And we will use the three of these to make a plot in the next part.